decreasing without looking at the function. Obviously it's a parabola, you know it looks like that. You know, here it is, you see it? But like, how can I figure that out without doing anything with the graph? You know, or if it was another difficult problem, how can I do that? Okay, well I can take the derivative. The derivative equals 2x minus 1. So, again, I just graphed a graph of the derivative. I didn't even have to do that. But I know the derivative equals 0. I can set it equal to 0 and then solve for x, and I'll get 1/2. And the only time you can change, this graph can change from positive to negative, is either the derivative has to equal 0 or undefined. It's the only times you can change from positive to negative. Do you guys agree with that? The only time you can change, you can actually have it change from positive to negative, or the original function changing from increasing to decreasing, is if the derivative 1 equals 0, because you have to cross through the line to change from positive to negative, or if it was undefined somewhere so it can jump up there. Yes? Okay, so that's it. So if you have some derivative like 2x minus 1, and I'm looking at this, I have no idea what the original function looks like. Here's my derivative. I solved, this thing is never undefined, so I don't have to worry about that. I set it equal to 0, and I solve, okay, I got x is 1/2. Okay? So I got a 0 here. So when x is 0, when x is 1/2, the derivative is equal to 0. Okay? Now I'm just going to check to the left and to the right. If I check one value to the left of 1/2, like 0 is to the left of 1/2, is this thing going to be positive or negative? Yeah, the whole thing's negative over there. Okay? If I check, do you remember doing this in the sign charts last year, Rafi? This is why we did it. Because we're going to build these. If I check one value to the right of 1/2, like 5, is the derivative going to be positive or negative? Positive. Yeah, and there's no other place. That means all of them have to be positive over here, and all of them have to be negative over there, because it never equals 0 ever again, and it's never undefined. So the only place it can change from positive to negative is here. So you don't have to check anywhere else. Does that make sense, Jessica? And what you can do with this then, check this out, Joanna. What you can do then is say, okay, that means the original function had to have been going down, then going up. Which means this has to be a min. Do you see that? You can make a little sort of like wibble-wobble sketch. You know what I'm saying? Like up, down, up. That's a min. Does that make sense, you guys? So first you determine when the derivative is 0 or undefined. Again, that's the only times you can ever change from increasing to decreasing, or anything like that. Okay? And then you just make a little chart. Is the derivative going to be positive or negative? Where is it increasing? Where is it decreasing? And you start just making a little chart of it. Off the chart, now you can determine what is the min or the max. Okay? How do we like this, Anna? Okay. Yes? Okay. I was going to say one other thing with this, but I forgot. Oh, so, and then if you want to write interval notation when it's increasing or decreasing, so it's increasing, and again, I include, it's right here, increasing, I include the endpoints, you don't have to, like there's two different schools of thought. I said this is increasing from 1/2 to the right, because that's what this is showing right here, after 1/2. And it's decreasing all the way from negative infinity all the way to that 1/2, looking left to right. Okay? And then with my extreme value, I can plug it in, or the location of it, I can plug this back in to the original function to find what that min value is, what the actual value is. Does that make sense, you guys? So it's a couple pieces together. You know, it's using that extreme value theorem. What's the extreme? Sandy, are you okay? Are you sick or something? Why don't you go get a drink of water for me? Make sure you're okay then. Okay, good. Make sure you're all right. Okay. With the extreme value theorem, it lets you locate. It shows you how to locate your mins and maxes. Okay. With your mins and maxes, or like where those extreme values can only happen when the derivative is 0, when the derivative is undefined. And now you can use stuff like this, the intervals increasing and decreasing, to actually determine, again, without looking at the graph, if it is indeed a min or a max. Okay? Do we like that or no? Sounds like a yes. So again, they have a couple other kind of random neat things in here. So we'll just go over them. Again, if the derivative equals 0, if you know the derivative equals 0 at each point on some interval, then the original function had to have been some constant, like f of x equals 5. You know what I'm saying, Chris? Because then that's the only way the derivative could equal 0. So there's 5. There's f of x equals 5. Again, you can do a secant line just like we did the absolute value of x function. You know, you took any, you have the point 1, 5, and 3, 5. y2 minus y1 over x2 minus x1. It's 0. All the tangent lines, all the secant lines, they're all 0. All of the slope is 0. So here's something good. Here's a little spoiler alert, second semester spoiler alert. You got two functions, and you know their derivatives are the same. You got f prime of x is equal to g prime of x at each point on an interval. Then the only thing that's going to separate them is a constant. For example, here's f of x equals x squared, and here's x squared plus 3. Both their derivatives are 2x, yes? What that means is, where this thing is increasing and decreasing, if I made a little chart, you know, like here, 2x, the derivative, what's the critical points of 2x? Yep, it's never undefined. I set this equal to 0, so x equals 0. To the left, what's the derivative? Negative. To the right, it's positive, which means the function had to have gone down and then up. So again, we can get all this up. All of this spacing is the same for both of these graphs because they have the same derivative. I know a lot of the same information. The whole left-right idea is locked in. I know exactly what's happening left to right. The only thing I don't know is that constant. Because it could have been x squared. It could have been, what is this one? X squared plus 3. It could have been any constant value, like x squared plus c. And that's what we're going to call it in second semester. What we're doing, this is the Friday night game. What happens Friday night? This is the games we play, okay? We're having fun. So what we're doing is undoing the derivative. We're finding the antiderivative, okay? And it's this whole process, you know, it's the anti-differentiation, antiderivative. It just means what was the original function, okay? And what we'll use as a lot of notation is this big f of x, whose derivative then is f of x. Again, that would be the antiderivative.